Okay, so what we're going to do here in this short video is we're going to kind of do what I would do if I had access to a whiteboard and kind of show you visually what's going on with some of these different data structures that we've talked about. And also you'll see why for some of them they work better for certain situations and others work better for other situations. Okay, so we'll start with the one that the array/array list. So you guys learned about arrays last semester, and you've learned about array lists now this semester. Okay, and so basically, if you remember, an array list is just a series. What we call the special word we used was a contiguous set of data. So basically, it's just here's like an array of like 4 items, right? And if you remember, okay, it's 0 indexed, okay? So here's how we would do the index locations, and the values can go inside of this little box, these boxes here, right? Okay, so the thing with arrays is we can access each individual item very quickly. So basically what it is the thing at the source array spot. So let's imagine we just had this an integer array, and I'll just 3.141. Okay, so it's like pi kind of, right? So these are our values in our array. Okay, and what I'm going to do is I'm actually going to add a 5th box here for something we're going to do in a second. So imagine that each array spot is just a value in memory. So this is an integer, this is an integer, this is an integer, this is an integer, and so forth. And the way that we access this is we just say, give me the thing at the base memory location. Okay, if we were to say, I want the thing at index 2, then the only thing that happens is we just add whatever, however much space each of these takes, okay, and we just add 2 times that to 0, to our base of where our array starts, and we say, just give me the thing at that index. It's real quick. It's just a base memory location, which would be wherever the 0 index is, right? Plus I will say I is our index, whatever index we're looking at, times whatever the amount of memory space for each individual item is. Okay, so we just take that calculation and we say, give me the thing at this memory location. All right, it's a simple calculation the computer does. It says, give me the thing at this address, and then the computer goes and gets the thing at that address. Okay, now the problem with arrays. So, well, let me say the good thing with arrays is we can put items, we can change values, like we can change the thing at index 2 very quickly, very easily. We can set an empty value. So if we wanted to put something here in the last position, right, then it becomes very easy, right? If we want to get a value from a specific place, that's easy too. That's very quick. The problem comes into play is what if we want to what if we want to insert? So let's say what we wanted to do was insert a new value into the front of the array. Okay, so we want to add a new value to the front here. Okay, but we don't want to lose all these other values. We want that to act kind of like either a queue or some other structure, where what we want to do is we want to add a value here into the first space, but we want all of these values to get moved along. Okay, so how do we do that? Well, what becomes the difficult thing is what happens is this has to be copied into here. 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 And then finally we can put our new value into this position here. All right. So how many copies have to be made? Well, it depends how many items are we having to move. However many items we have to move, that's how many copy operations have to be done. Okay, so arrays, array lists, good for, okay, so if we maybe say a green color for good, access is fast, right? Changing a value, fast. Let me go red for some bad things. Changing a value is fast, but inserting, slow. Okay, removing, and what I mean by removing is not just changing a value to 0 or something. That's terrible spelling. But removing is slow. Like, what happens if we wanted to remove a specific value? Let's say we want to remove this value here in the index 1 position and move everything else forward, right? So now this has to be copied into here, this has to be copied into here, this has to be copied into here, and n copies have to be made. Okay, so that becomes slow to do it that way. Okay, so arrays, array lists, good things are getting access to a value very quickly at a certain index, changing a value at a certain index very quick, but inserting or removing and keeping the old values and just kind of moving them along and maintaining position becomes very slow. Okay, so let's talk about another new data structure we talked about. Okay, do this as a kind of an orange color, was a linked list. And so the basic idea of a linked list is what we have is we have a node that has a value. I'm going to draw the basic idea up here. Hold on. Has a value and then has a link. Okay, so, or a pointer. And what happens is that basically that when we create a new node in our list is we take the value, whatever it is, so let's say 3 is our first value, and then the link points to the next value in the list. Now, I'm not going to do the doubly linked list here because that's a different data structure, and you saw that in the lecture time. You saw that with the way that Java does a linked list, implements it. You'll learn more about that in your data structures class, but I want you to understand the basic idea of a forward-pointing, single direction linked list. Okay, so what happens is we have this pointer called a head. It's the front of the list. Okay, and just like an array has that base, so the same thing with that array list structure has a base memory location, which is the first position in the array. The head points to the first value in the linked list. Okay, if we have nothing in our linked list, if we have not put in any values yet, we have an empty linked list, then the head points to this special value null. It's just null. It's nothing. Okay. All right. Once we insert a value into our linked list, the head points to that new value, and the list points to this value null now. Okay. I'm not going to draw null here because I'm about to change this up quite a bit. All right. So, but for now, if we just have a single value on our linked list, head points to the first node, and the first node's link points to null. Okay. Then we want to insert a new value into our list, or we want to add to the end. Well, we go to the end of our list. We add a new value. Its pointer now it points to null. Okay. Do it again. Okay. Now, the way that we get to the end of the list, unlike an array, unfortunately, we can't just go to the end of the list. Okay, you can't just do that. Okay, what we have to do is because the only thing we have access to is that guy right there, the head. Okay, it's the only thing we have access to. So we have to go to the head, And we have to keep going. If we want to add to the end of a linked list, we have to keep going. We have to go from the head to the first node. From the first node, what does it point to? It points to a second node. What does it point to? It points to a third node. What does it point to? It points to null. Now, once we find something that points to null, we've reached the end of the linked list, and we can say, okay, I want to add to the end of this list a new value at this place here. Okay. And I'm going to go ahead and write null here now because we're about to do some fun stuff with inserting and removing. Okay. All right. So now what happens if I want to access a specific value? Let's say I want to access the thing at index 2, for example. So if we look at it as being this would be considered index 0, this would be index 1, this would be index 2, this would be index 3. Okay. If I want to access the thing at index 2, I can't just go and get that from some calculation in memory. What I have to do is I have to start at head. I have to go to index 0. You have to go to the thing at 0, the first thing. I have to go follow its pointer to the next thing. Follow its pointer to the next thing. And then I can get the thing that's there. Okay? All right, so that becomes a little bit more difficult. Access, as you can probably already tell now, I'm going to use red for, remember red is our bad color, right? Is our not good, right? Or slow. So access of a particular item at memory, except for the first thing in the list. Anything that's early in the list, anything that's early, like in the first couple of positions, especially once the list gets really long, anything that's early is easy to access, is quick, somewhat quick to access. But if we want to get to like something later, towards the end of the list or towards the middle of the list, then it becomes slower to access those things. Okay. But the or change and then changing. Okay, and then changing in the same way. Changing a value. If I wanted to change the value of the third item in this list, I've got to navigate to the third item, and then I can go to then I can change that value once I get there. And these two, changing and access, they're both slow for the same reason, is that we have to get to the item before we can do anything with it. Okay, now, however, so let's talk about something that linked lists are good for, and that is for inserting. Okay, so if I wanted to insert, let's say I wanted to insert a new value at the front of the list, okay, just like we did with our array. So I want to insert the x value. Well, what I do is I can create this node with some value, okay, and then I say, okay, now I want your pointer to point to that thing. And now remember, there's nothing wrong with this, right? We can have two things that point to the same object in memory, right? There's nothing that stops us from doing that, all right? When we no longer point to something, that's when we lose it. That's when it's no longer there. And then, fortunately, again, as we've talked about before in lecture, Java has this thing called garbage collection that cleans that up for us, and it doesn't just keep it out there in memory. Okay. Now we haven't inserted it yet, right? Because head would still point to this first thing. So what we do is we create this new node, we take its pointer and point to the first value in our list, okay, and then we say, okay, now you head, you're not going to point to this 3 anymore. You're going to point to x now. Now what's happened is we have inserted very quickly a new item into our list. New node, pointer, done. And all of this stuff has moved along automatically. We haven't had to copy multiple new data into new places or anything like that. It's all just moved along on its own. And guess what? Removing an item becomes even more simple, right? Let's say we wanted to remove this item right here. We wanted to remove the 1 item, okay? We don't have to navigate to it. We don't have to copy anything over it. None of that has to happen, okay? The only thing we have to do is we simply say, 3, I don't want you to point at 1 anymore. What I want you to do is I want you to point at the thing that 1 is pointing at. Okay? Take this. It's no longer pointing at 1. It's now pointing at the thing that 1 was pointing at. Okay? And now guess what? Nothing's pointing at 1 anymore, is it? All right, nothing's pointing there anymore, which means a 1, we can't get to it anymore. It's gone. Garbage collection will come and clean it up, and now we have a new list that I will change to this. And this is now our new list, right? We don't have this 1 in there anymore. Okay, so what does that mean? That means that inserting and removing becomes very fast. Right? Becomes very fast that once we get to the place where we want to insert or remove something, a linked list, very, very fast. Okay. All right. So wrong thing. This is what I want. Okay. So let's talk about this whole stack and queue thing too. Okay. So what I was trying to get at, and I'm not sure if I came across clear in the lecture discussion, was if we think of a stack like this, okay, and that each time we put something onto the stack, all right, then we're just pushing it onto the last location, right? Okay. Then an array becomes a very easy way to implement a stack, right? Because we're not moving stuff around. We're not having to copy new values into new places. None of that has to go on, right? The only thing that has to happen is we have an array or an array list. We add to the end. So if we want to push something onto the stack, all right, if we want to push something to the end of the stack, we just take whatever the current size of the stack is, and we just set the value at that position in the array to that new value we're pushing, and then we just get whatever the last value in the array was. Okay, and then we just decrement, we remove the size value, right? It becomes really easy to implement this using an array. Okay, linked list is not out of the question either. You just kind of just adds it to the front of the linked list. Pop removes the value from the front of the linked list. But if I was just doing this for just for fun, or just as a trying to understand these data structures, stack, I would probably go ahead and do it as an array, because an array doesn't have a lot of extra stuff. You just have all these memory locations is all. Whereas with a linked list, there is an extra overhead of the pointer. There's the value, there's a place where we hold the value, but then there's also the pointer to the next value in the list we have to talk about. Okay, so go for the simpler data structure. Go for the simpler implementation if it works well enough. Okay, but for a queue, on the other hand, I would probably not do this using an array, and the reason why is because Switch this to a different color. Okay, I would probably not do this using an array, and here's why. Imagine that this is kind of my array position. Let's say we had this size 4 queue. Okay, the way that the queue works is first in, first out, right? So if we service, right, if we service this, we add a new value to the queue, right, then the first in is 3, and I need to service 3 next. Then if I do this and then this, right, now if I need to service 3 next, well, if 3 comes out, if I serve that, now the next value that I have to serve is this one here, right? So if we think about it as when the queue first starts, when we start putting values into our queue, right, then the next serviced index is going to be what? It's going to be 0, okay? And the last is going to be whatever the last place that we inserted into. So let's say at this point the last would be 2, okay? Now, what happens when we serve 3? When we serve this first value, the next becomes what? Becomes 1. So the next is 1. The last still is 2. Now let's say we serve this one. The next is 2. Last is 2. Now let's say we add 1 to the queue. Another person comes and gets in the queue at Migros. Last becomes 3. Oh, I wrote this wrong. Sorry about that. Okay. And this is where it gets interesting, right? Because now, let's say that someone else comes to get in the queue. Another item comes to get into the queue. We've run out of space here. We don't have another block to put them in, but we do have empty blocks here and here, don't we? So we could put them into a place, but the problem is how do we change this to 0? How do we go back and say, okay, we'll push something into 0? Well, then what requires is all this this fancy arithmetic involving the modulo operator based on the size of the queue, and that just becomes a little bit more difficult than is absolutely necessary. Okay, and so it is a possible implementation. I'm not saying that it's not, but it just requires more work than another option might do. And the option that I would probably more suggest would be something more, again, like a linked list. So here we head points to this. This points to our next value. This is going to point to null for now. Okay, and then what happens when we want to serve? Let's see, go ahead and put 4 in there actually. What happens when we want to serve our next customer, our next value? We simply just take this and point it here now. We return this value and we change what head points to. All right? Then we do it again. We say we want to serve the next value. All right? And we just change what head points to. Now we want to add something to our queue. Okay? Now we want to add something to our queue. We don't have to do any of this fancy arithmetic, right? We just add another value. Right? We want to service another one. We want to dequeue. Done. Right? There's no fancy arithmetic, no creating this circular buffer thing, none of that. Right? We just get straight to just service the first item in the queue, add something to the end of the queue. All right, at the linked list. Okay? So this is just some different ways that you could use the same. You could use some of these data structures, this linked list, arrays, and array lists, and to implement stacks and queues and stuff like that. So I hope this has helped you in some way. I hope this has helped you clear up some questions you might have about how to use some of these structures and how these structures are implemented. And again, if you have any questions, let us know. You'll probably look at some of these data structures in your next lab, and we will move on into some other, we'll look into sets and maps in the next week. And so make sure you understand these data structures because your final assignment will incorporate them. Okay? Thanks, and çocuk bayramınız kutlu olsun. Sağlıklı kalın.